My name is Ralf Omberger. I'm applications engineer at MPS. I'm located in Ettenheim, that's in the southwest of Germany. We are talking about ideal diode controllers in automotive systems. Today, first the introduction, then the question, what is an ideal diode controller? Power and voltage drop of ideal diode controller versus a Schottky diode. Then I show 3 different types of diode controllers, our MPQ 5850, the MPQ 5852, and the MPQ 5816. Then we show practical measurements. The main function is the rectifier function with an example on AC superimposed alternating voltage, the reverse polarity in different automotive tests. Next application will be the Oring application, how to parallel batteries and power supplies. And then we do a quick comparison between a P-channel MOSFET solution versus the ideal diode controller. Following by EMC and layout recommendation, part selection, design and measurement tips. The webinar should help you to design an ideal diode controller. We will give you some tips and we do a comparison between different solutions. What is an ideal diode controller? On the left side, you see the most common solution. It's a passive Schottky diode, and it's just a rectifier. The main problem with this circuit is you have a large voltage drop across the diode, typically 300 millivolts to 800 millivolts. It's depending on the current which is flowing through the diode. On the right side, you see our ideal diode controller. It's an N-channel MOSFET with the source connected to the battery and to the AC source, and the drain is connected to the load. And this N-channel MOSFET is controlled by an ideal diode controller. The big advantage of this method is the voltage drop between source and drain is only about 20 millivolts. And it's current independent as long the RDS on is not too big. When the RDS on is too big, then of course at higher currents, you have the multiplication between RDS on and the current. Then the voltage drop rises to a higher value. Here is the main advantage. The power of an ideal diode controller versus Schottky diode. You see here the current. I applied here 1 ampere up to 7 ampere. And with a Schottky diode, we have a steep curve. It goes at 7 amperes. We have a power loss of approximately 3.5 watts. That's very much. This curve is taken with a 5 ampere Schottky diode with a peak current specified 100 ampere and a reverse voltage of 60 volts. This diode is really a large diode already. It has a package of 4.7 millimeters to 2.5 millimeters. And it's specified at 4 amperes. It has a 1.5 watt power loss, and the T-junction already rise to 150 degrees. It was measured around on a PCB with 2 centimeters times 2 centimeters copper for the anode and for the cathode also. And here we see at 4 amperes, we are already at the maximum of the diode. In comparison, a MOSFET here at 4 ampere has only around 100 milliwatts. Because the MOSFET is controlled to 20 millivolts source to drain voltage drop. And everybody who makes electronic knows very well this high power, 1.5 watt, 1.7, you can't apply in a standard PCB without a special cooling, which is it's non-realistic for a commercial PC and for an automotive PCB. That's why it's the big advantage. The low power loss in the MOSFET compared to any Schottky. Here's the curve of the voltage drop. The comparison of an ideal diode controller to a Schottky diode. It's just a reminder of the last slide. Very comfortable with the MOSFET as rectifier. Here we go to our first part, the MPQ5850. It's a diode controller with an external MOSFET. It's an N-channel MOSFET. The gate is driven by a gate booster circuit with these two parts. The MPQ58 has as features -36 volts to 42 volts, the low dropout regulation voltage of 20 millivolts from here to here. It has the gate boost converter circuit. It's a tiny inductor, only 68 microhenry. You can use the smallest one you find on the market. It will work. The gate drive capability is 430 milliamperes. Current into the gate, and the gate sink to discharge the gate 170 milliampere. The standby current, when it's not enabled, it's 4 microamperes, and the steady state, this means when the device is running, 30 microampere. And there is a power good function to show you if the supply is okay. It's delivered in a T-SOT 23.8, it's a small size, 2 × 3 millimeters. Applications, all automotive applications, and battery powered systems like Oring or swapping. The typical application where this part is made for is the LV124, the AC superimposed alternating voltage. The load dump can be applied directly to 42 volts. A cold crank is possible down to 0 volt. It's protecting against reverse polarity. When you change here. And it's protecting against transient ISO pulses. Another part we have, it's the MPQ5852. It's a pre-release part, so you can also get already samples of these parts. It's a diode controller, also with external MOSFET, plus monitor function. By principle, it's the same like the 5850, but with the addition of the monitor functions. And the monitor functions are, it's a control for undervoltage, overvoltage of the battery voltage. The battery voltage sensing, it gives out a measurement value of this input voltage. It has an overtemp warning for the T-junction of the IC. We call it a fault indication. We have a fault pin here. This pin can go high or low, depending on the conditions. It's functional safety specified. We have the documents for it. It's a only 3 × 3 millimeter circuit. Applications the same as 5850, full automotive, battery powered systems, and of course it's also specified or made for the LV124 test series. So here, the circuit here is an example for a 20 ampere output current. The MOSFET can rectify up to 100 kilohertz. The next part we have is the MPQ5816. It's a diode controller now with internal MOSFET and with included charge pump. You see here, the MOSFET is, you don't see a MOSFET, it's inside. It's a 10 milliohm RDS on MOSFET and can rectify also up to 100 kilohertz. This circuit here and the MOSFET has a dimension for up to 9 ampere E out. By principle, it's a similar rectifier to the other parts explained before. The negative voltage is increased up to minus 40 volts and can start up from 3 volts to 42 volts. The gate drive is also high, but it's an internal signal. Steady state, 75 microamperes. And also with a long list of monitors. Monitor load, monitor battery, battery voltage sensing. This sensing means it's a 1 to 10 divider from input to output. The thresholds are selectable, overcurrent warning, overtemp warning, fault indicator, functional safety documents are available. Made for the same applications, it covers the full automotive tests. Let's go to the first scope plots. I choose here the rectifier function AC superimposed alternating voltage. We apply here the yellow voltage, that's the V in. It's for an example, a 1 kilohertz DC from 8 volt superimposed with an AC 1 kilohertz up to 13 volts. And the red one is the rectified output. You see here the blue one is the input current of the device. Here is no current into the MOSFET. And here, when the gate goes on, that's the green one here. It goes from, it switch on fully from 0 volts to 12 volts gate. Then, of course, the output capacitor. In that case, it's a 470 microfarad electrolytic. It is charged quick. Here it's full. It's still a little bit charged. And here, when the V in goes lower, V out, the gate offs quickly. And from this moment here, the input voltage goes down, but the load is still supplied by the 470 microfarad capacitors in this range. You see, it's a straight line. It was a constant output load applied, an electronic load. It's a simple function, and this measurement explains it very well. The next example is a little bit more difficult to understand because here we increased the circuit. We added here on the output an LC filter, 4.7 microhenry, plus a 1600 microfarad electrolytic on the output. On the input of the filter, we have a small 10 microfarad MLCC. And then, of course, the conditions are changing. We are applying here 20 kilohertz AC superimposed. And then, depending on the dimension of L and C, we get here the DC voltage. In that case, it's 6 volt DC output. And here the input goes down to 3 volts, and it rises up to 9 volts. So the DC voltage we applied is around 6 volt, and we also have it on the LC out signal. The LC out signal is here. And this is what we want. We want to have a DC voltage after the rectifier and after the LC filter. And this is already 20 kilohertz, and this method is functional up to 100 kilohertz. We see also here the input current. That's the orange line. In this combination of filter and load, it's always positive. We have here the green line. That's the current in this capacitor, in the MLCC. We placed here the LC filter because the L is very necessary to prevent the electrolytic from such high currents here. Everybody who is making LV124 AC superimposed knows very well the electrolytic gets easily very hot under this test. And with this configuration, the electrolytic becomes safe, and only the MLCC sees the alternating voltage here, the rectified alternating voltage, but can withstand these high peak currents more easy than the electrolytic. So this is a typical filter we recommend for automotive systems. Sure, the size of the capacitor depends on your load current and also the size of the inductance. It must not be 4.7 and it must not be 1600 microfarad. But it is a must. You should have at least minimum 10 microfarad ceramic here on the output. Here we have another example. It's a little bit more difficult to understand because here we have also the switching action of the gate. The gate is the green one. Here it's full on, 12 volt. It's switching off to 0, on, off, a short oscillation, that's normal. It's based from hysteresis from the comparator, and again on, off. Why the gate is offing here? It's because we are coming in a condition where the E input, that was here, is going below 0. And in that case, we want to prevent that current is flowing back into the battery. That's why we just off the gate. And you see here the drain voltage is still supplied backwards, in that case by the energy of the inductance. But the most important thing is the the VLC out here, the output DC voltage, it is still a DC voltage. And this is what you want. It's a clear VLC out because of the CLC output filter. And we have no current back into the battery. A quick explanation about the red signal one here, the small one. It's the I boost inductor. That's the current in the in the gate booster, in the inductance, is around the peak here, around 200 milliamperes peak. And every time when there is a gate action means the gate of the MOSFET requires some fresh new current into the gate or discharge. And this, of course, takes energy from the gate booster. Here, the gate booster is living from the reservoir, but here, the gate booster is charging again new energy. But it's always the same. Only 200 milliamperes peak approximately. And your inductance for the gate booster must deliver only around, well, let it be 30 milliamperes RMS current. It's like nothing, so it can be a very, very tiny inductance you find and have to withstand the 200 milliampere peaks before it's going into saturation. And you see here, it's a clean triangle. It's not a saturated inductance. Here we have another example. We have here the reverse polarity test. It's taken from the LV124. It's called the E15, and it's going from 12 volt. That's here. The yellow behind the blue, it's 12 volt here. The reverse polarity becomes active to minus 14 volts here and back to 12 volt. It's just an alternating reverse polarity. What you see here is the input current. It's 10 amperes here, goes down to 0. No current is flowing back into the battery. Again, the gate is on. The polarity is plus 12 volt. We have again 10 amperes, 0 ampere, 10 amperes. You see here also the gate to source voltage. For the 10 ampere, this MOSFET requires a gate to source voltage of 7 volt. For the controlled 20 millivolts, source to drain voltage. So it's still in regulation with this MOSFET for the controlled 20 millivolt drop. We see also here the green one, that's the V rest to ground. It's around 23 volts. That's the voltage across the 1 microfarad capacitor for the gate booster. It's just the power supply of the gate booster, nothing more. This is a supply you always should monitor when you do such experiments. Then you see the IC is working fine, has enough internal power for the gate. And you see here also the I boost inductor has no current in the reverse polarity condition. And when the gate is coming back, when it's going to positive to the 7 volts, then of course it needs some energy to keep the gate voltage at this 7 volts. Here the message is no current back into battery, and the output voltage, which is the V drain, is 0 volts, even when the input voltage is minus 40 volts. Which automotive tests we have in the LV124 specification? Our parts, they are designed to pass automotive LV124. These are the typical tests which can be applied for the diode controller. The long-term overvoltage, transient overvoltage, transient undervoltage, the jump start, load dump, the superimposed alternating voltage, slow decrease and increase of the power supply, the quick increase of the power supply, the reset behavior, start pulses, reverse polarity, and the transient positive and negative pulses of the ISO tests, which are also part of the LV124. Another important application for the diode controller is the O-ring. The O-ring is connecting of two or more power supplies to one load. We see here the V-in-1. We have here the diode. I made here the symbol of the diode of an ideal diode controller with a drop of 20 millivolts. And then the current is flowing through the MOSFET into the load. This is drawn for the case when V-in-1 is bigger than V-in-2. And then here, this MOSFET is blocked, then we have 0 amperes. In case this voltage becomes bigger than this one here, then the current is flowing this way. And here we have 0. It's just the method of the O-ring, and this can be, it is expandable to multiple sources. The diode controller protects the power supplies from reverse currents. It is a hot swapping. You can do it alive in a live system. Always the highest voltage supplies the load. In case when you adjust the voltages to the same voltage, then the load will be shared. Then you have 50% from here and 50% from here. Here we have a scope plot for the O-ring when we are removing the V-in-1. The V-in-1 has 12 volt. It's the yellow trace. Here at this moment we off the power supply and it goes down to 0 volts. But the other voltage, that's the V-in-2, has also 12 volts here. Then the output is still 12 volt. You see it here easily in the currents. This current and this current here. Their share equal 1.25 amperes. The E-in-1 goes to 0 here. When I switch off, 0. And the other one overtakes the full current to 2.5 amperes. And you see here also there is no reverse current back into the switched off V-in-1. Here we see the calculated power on an R load of 4.7 ohm. This resistor carries on the beginning where both supplies are on 30.4.8 watts, and after switching off, the power is almost the same, 30.3 watts. And this is exactly what you want. Whatever you're doing here, hot swapping on the input, you have a constant output voltage. In that case here, 12 volt, 12 volt, 12 volt. Constant output power, no matter what you're doing on the input, in case it is the same voltage. The next example is an O-ring on-off when there is an offset on V source 1 and V source 2. We have here the source 1, that's the V-in-1. It goes from 12.4 volts down to 10 volts. And we have the V-in-2, the red one. It goes from 12.4 volts to 10 volts. And here you see the V out. It's still 12.4 volts. Exactly, it is 12.3.8 volts because there is the 20 millivolt drop missing from the MOSFET, the drop between source and drain. And here we just switch off, on, 10 volts, on. And here you see the results in the currents. E in 1, E in 2. But the E out it's constant. P out is constant, 6.2 watts. And here the gate voltages to explain it better. Gate source 1 here goes 0 here. When here it's going to 10 volts because this source cannot deliver current. It's just an easy game. Here we have another example for low voltage sources in an Oring application. We have here a V source of 2.889 volts. We have a second voltage of 3.41 volts, and we switch off 1. And then, of course, here, the V drain here it's delivered by the 3.451 volt minus the 20 millivolts, switched off, and then the yellow one overtakes with its voltage here, with the 2.889 minus 20 millivolts. But this one here is the output voltage. And then, of course, on a 10 ohm load, you have the currents depending on the V in and V1, which one is active. And it's a good example to show that the part is working also at low input voltages. The limit is 2.6 volt. When you go lower than 2.6 volt on the V drain, then you force the part in a reset. Then you have reached the condition of the under voltage lockout. Here is a little bit a difficult example. Let me give you this scope plot as a homework when you have downloaded the presentation. It shows an IC start from an under voltage lockout. I explained each spike and each action with a comment. The typical startup time is only around 1 millisecond. The message of this is, please always supply the V drain and keep it higher than the under voltage lockout based on your load and on your output capacitor. For example, when you do a cold crank and when the output capacitor is not big enough, you have to increase, especially then when the V drain is going below the under voltage lockout to prevent the IC to go into the reset, which is typically 1 millisecond. Because when the IC is in a reset condition, then the gate cannot be active. There is no power, there is no energy for the IC to boost up the gate voltage. This means you still have the current flowing from the input to the output, but you have the voltage drop of the body diode, of the parasitic body diode of the N-channel MOSFET. And this you should prevent because it can make the MOSFET hot in case you repeat this condition many times, frequently. Here we have the comparison between passive P-channel MOSFET rectifier versus an ideal diode controller. Let's start with the right side. That's a diode controller. You know this image already from the beginning. It's a similar condition. We have here the input voltage. It goes from 0.5 volt to 12 volt, but the output is still a DC voltage plus a small AC. This is what you want. You want to have a DC on the output, and it's not a funny AC from the input on the output. And the diode controller does this very clear. You have a quick gate on and a quick gate off, and the peak current charging the electrolytic. On the left side, you see a similar condition measured with a P-channel MOSFET rectifier solution. You see also here it's working, of course. It's switching off here the gate. It's a negative gate, it's a P-channel, of course. Here overtakes the output capacitor, the load. But you see here very clearly it's not a sharp waveform, and there's a voltage drop between input and output. And this means power and heat in the P-channel MOSFET compared to such a diode controller solution. The problem with the P-channel MOSFET rectifier is these are typically often very simple circuits, two Zener diodes and a few resistors, and that's all. And you cannot do such a good control loop like we do it here with the IC. So you will always have the heat problem with the P-channel MOSFET under AC. Okay, in certain operating points, you can improve the Zener diode and the resistor circuit. But when you have a wider range of the V-in, it's only from 7 volt to 30 volts, you are in trouble with the circuit. You have here a small usable V-in range only, compared to here a wide V-in range. It's problematic under AC waveforms. With the diode controller, it's nothing. It's easy for the part. You have a higher MOSFET temperature. Here you have a lower MOSFET temperature. You have higher cost for the P-channel MOSFET compared to the lower cost of a typical N-channel MOSFET. Why we use a gate booster and why we use a charge pump. The MPQ 5850 and the 5852 with the external MOSFETs, they are using a gate booster. We did this because the gate booster can drive a wide range of external N-channel MOSFETs of different sizes. The gate booster can easily output lower and higher gate voltages, and the gate booster enables large gate currents as well as fast rising and falling times for the external MOSFET. In other words, you can use a MOSFET wherever you like, it's working, because the gate capability is large, it's big for any MOSFET. The internal MOSFET, which is used on the 5816, there we use a gate charge pump. We did it to save the small inductor. But in that case, sorry, when we have an internal MOSFET, we know very well which MOSFET is built in. We know the curve characteristics of the built-in MOSFET. We know the gate capacitance of the built-in MOSFET, and therefore we can design the charge pump exactly special for the built-in MOSFET. Typically, it's more easy to drive a wide variety of external MOSFETs with a gate booster. That's the only reason why we use the gate booster and not the charge pump. We use the charge pump only because we know here the internal MOSFET very well. It's part of the IC. Does an ideal diode controller create EMC problems? No. Just no, only a very little. The gate booster and the charge pump have the highest activity at the transient gate load. When the gate is quiet, the gate booster comes only with a few kilohertz. This is just sometimes. Under a high gate activity, for example, when you have AC superimposed, then of course the gate is always going high, low, and to bring the current for the gate, then of course the gate booster must run always continuously. This means you have many times the 200 milliamperes peak in the inductor, but on the other hand, what is 200 milliampere for EMC? It's like nothing. When it's coming in the kilohertz range, maybe up to 100 kilohertz maximum. And the size of this inductance is very small. It's tiny. It's around 2 millimeters to 2 millimeters and have a heat of 1.5 millimeters, 2 millimeters, whatever you choose. There is not much field radiating from this small, tiny inductance. And when you are in an EMC chamber, when you are measuring the EMC measurements, they are specified for a clean DC voltage. You don't measure under LV 124 conditions the EMC of your control unit, of your load. When you measure this under LV 124, then you have other problems. Your power supply has a fault. When you have the AC overlaid, then the EMC is not the problem. Then the problem is your power supply. So the charge pump and the gate booster is almost no problem for the EMC. We have this question often, that's why I explained it here. Make a check on the data sheet of our devices. You will see that the measurements, it's close to the measurement, close to the noise level of the EMC receiver, and therefore unproblematic. Does a diode controller require a special PCB layout? No. You have to consider only a few points. Play the capacitor for the gate booster or the capacitor for the charge pump close as possible to the package. That's all. Then place the switching inductor of the gate booster close as possible to the package. Route the trace of the gate short such that it is encapsulated with ground. In other words, put it on the inner layer or put ground near the gate. It should not be a problem. The gate wire is short and it's easy to route. It improves the radiated immunity to the circuit when the gate is shielded with ground. Place the bypass MLCCs close to the V drain and V source pins. There's one on the V source, it's a 10 nanofarad. Place it close to the V source pin and place at least 1 microfarad ceramic on the V drain pin or the 10 microfarad, whatever you prefer. Place the copper polygons near the external and internal N-channel MOSFET. The PCB copper polygons are the heatsink for the components. For the external MOSFET, the polygons cool down the MOSFET, and for the 5816 with the internal MOSFET, you need some vias near the package to cool down the MOSFET, which is internal the diode controller. Here's an example for layout. This board here is for the 5852. It's made on a 4-layer PCB, and it is designed for 20 ampere output. You see here the polygons. They cool down the MOSFET, the external at 20 amperes, and cool down also a little bit the electrolytic and the inductance of the CLC output filter. Of course, you choose the polygon size and the number of the vias according to your Vout, to your output current, of course. For 20 ampere here, it's fine. Here you see the 5852, the tiny components around, resistors, capacitors. It's very easy to lay out. Just place them close to the IC, finish. To route a DC-DC step-down converter is much more difficult to understand, but this one here, it's just a simple game. How to select the N-channel MOSFET? Of course, to save the cost, use the smallest N-channel MOSFET suitable for your expected E-train, the output current. For a 12-volt automotive system, we typically used 40 volts to 60 volts, depending on your selected margin and on your transient input pulses. You can use also smaller MOSFETs with a smaller voltage. If you only have batteries, lithium-ion batteries or whatever, to 5-volt input voltages, it makes no difference for the part, for the IC. This one here is important. The ideal diode controllers, they are designed for standard logic level MOSFETs with a gate source maximum greater than 14 volts. It's because our gate booster has a maximum output voltage around 12, 13, 14 volts. Therefore, do not use logic level MOSFETs because they are having a lower V-gate source voltage. The maximum is around sometimes 10 volts, 9 volts, 12 volts. You would destroy the MOSFET. Only use standard logic level MOSFETs together with the ports. All MOSFET sizes are possible. A 10 nanofarad gate capacitance is possible, which corresponds. This is similar to a high power MOSFET, typically 1 milliohm 400 ampere. In other words, we can drive 10 nanofarad gate capacitance. We specified up to 10. We tested up to 50 or 20 nanofarad. In that case, the slew rate is reduced from the gate. This is also a question, comes often. MOSFETs of the same type can be connected in parallel because an increased RDS on due temperature produces feedback on the gate, which can help balance current sharing. But if possible, try to use a single MOSFET. It's easier for you to give the proof that both MOSFETs are running safe. It's depending on the tolerances of the MOSFETs to each other, if you can do it or not, and how far you push the output current to the limit of the MOSFETs. For our IC, it makes no difference if we drive one MOSFET or 10. It's working. But it's easier for you to use a single MOSFET. Some design tips. The wire harness helps to attenuate transient V-in waveforms. The parasitic inductance of the harness of the link, together with the 10 nanofarad V-in MLCC, creates a second order low pass, which is attenuating high frequency. When selecting the gate booster inductor, follow the recommendations in the datasheet. Consider temperature and the applied V-in max. There you will find there a diagram how to select the correct inductance. Measure for test the inductor's waveform current, the peak and the RMS current under a high gate activity. Measure this current, for example, when you are applying the AC superimposed test. Then you are sure if the inductor survives, if it has the correct specification. A shielded inductor is not required to pass the CISPA 25+5 because it's only a tiny inductance. This point here is very important when you measure on the diode controller. Have your focus with the oscilloscope always on a stable V-train. Watch it and use a sufficient capacity on the load, because you want there a DC voltage and not an alternating voltage, and you want to prevent the IC from going into the under-voltage lockout. It's about 2.6 volts, 2.6, 2.7. Under the reset condition, the gate is inactive for about 1 millisecond. Then in that condition, the MOSFET's parasitic body diode conducts. The diode then carries I load, resulting in a higher T junction of the MOSFET. And this sentence here is very important. The controller's internal VCC, the internal power supply for the IC, is powered from V-drain. It's not powered from V-source. That's why you have to keep the V-drain stable. And you have to attenuate radio frequency interference with a small bypass MLCC directly on the V-drain pin. The advantage for this is when we are supplied from the V-drain, of course, the V-source is free. It's designed for very quick changing waveforms and can withstand reverse polarity. So remember again, the IC is supplied from V-drain and not from V-source. That's why we can do on the V-source whatever we want. AC, negative voltage, it's working. It's the principle of the IC. The negative TVS diode on the V-in is required to prevent from a negative spike on V-source. This is physics. It has nothing to do with the diode controller. These negative spikes, they are generated when the MOSFET quickly turn off an load current. The rapid change in current creates a negative voltage across the parasitic inductance of the circuit board, of the PCB, and of the wire harness. And depending on the length of the harness and of the PCB, and of course of the current, the generated voltage can be higher than the absolute maximum ratings of the IC. It can be not higher, lower than minus 36 volt or more, minus 40 volts from the IC. And that's why you need also a negative TVS. One thing I forgot, you don't need the negative TVS in case you know very well which harness you are using in the application. When the PCB is finished and when you tested it very well, that the negative spike never reached the minus 36 volts. This is a matter of testing your board and your harness and your load and your operation conditions. But on the beginning of a development, please use also a negative TVS. To remove that negative TVS is a question at the end of your development, when you are very safe, when you are very sure what you need, which harness. Some measurement tips. A multi-channel oscilloscope is recommended for measurements on diode controllers. 100 megahertz bandwidth, it's okay. Better use a scope with more channels. You don't need the fast ones. When measuring V source with an oscilloscope, always measure direct at the V in or the source pins, because the fast signals will cause a voltage drop on the board and the wire harness. You are interested in the waveforms on the pins of the IC and not somewhere on the copper. For sure, refer to a ground near the IC. Testing transient V-in waveforms require a power amplifier with a fast slew rate. And this amplifier should be stable to drive MLCCs. Typically, an automotive test amplifier for the LV124 in combination with a harness can do that. Focus on V-train and V-source with the oscilloscope. Then use a differential probe or the MUD function of the scope to measure the V-gate source voltage. It's always good to monitor the gate voltage when you know it's on or off. It's an indicator if everything is fine or not. Then you must observe the supply capacitors, the VRES for the gate booster and the VCAP for the charge pump. It must be always higher than the drain voltage, and then typically it's fine. There's also an undervoltage lockout built in for the VCAP and for the VRES. You can read the data sheet about the details. The E source, the current into the MOSFET, is an important waveform. Try to measure it directly on the MOSFET's source pin. Note that the current probe in the wiring harness contains also the AC of the 10 nanofarad V-in MLCC. So when you measure, there's sometimes a negative current. It's most often the current coming back from this 10 nanofarad. It's not a current which is passing backwards from the MOSFET into the battery. Especially, of course, at higher frequencies, when the impedance of the 10 nanofarad goes low. Measure transient V battery waveforms with a differential probe, especially when using a long wire harness. At 10 kilohertz, 20 kilohertz or more, there's really a remarkable voltage drop on the harness. which is helpful for your test because you have a low pass from the inductance of the wire harness and this 10 nanofarad capacitor. Let's come to the conclusion. The MPQ 5850 from MPS is a solution for any N-channel MOSFET size. So far, it's a standard logic. The MPQ 5852 has the same rectifier functionality as the 5850, but with two additional voltage monitors, a fault indication, and functional safety specification. The MPQ 5816 shows a solution with internal N-channel MOSFET, two voltage monitors, fault reporting, and functional safety documents. The devices cover a wide range of applications from automotive, industry, computer, and battery management systems. The 5850 and the 5852 enable a wide current range with the choice of an external N-channel MOSFET. The 5816 is an outstanding product with an internal 9 ampere N-channel MOSFET. It is designed for minimum board space, reduced bill of materials, and simplifies purchasing. So I am on the end of my presentation. Let us know your questions from now. You can also find articles and videos on our website. And this link here below, there are a lot of information about diode controllers, technical information, an application note. I wrote also an application note with much more details than in this webinar about the 5850. You can find it here, and many other informations from my colleagues. So now I'm open for your questions. I hand over back to Julian. Thank you for listening. Welcome.
Thanks a lot, Ralf. Great presentation. So I want to remind you that you can mouse over the bottom of your Zoom webinar interface and you will see the Q&A button. You can type in any question that you might have. As we are waiting for more questions to come in, I want to remind you that we're recording the session and we will send you a link early next week. With the link, you can watch today's webinar on demand, and we will also send you a link to the PDF of the presentation. Please also check our MPS webpage and the webinar schedule to see additional sessions. And another topic, if any one of you is attending PCM in Nuremberg in 3 weeks, do not miss to visit us in Hall 7. So let's get started with the first question. And it is, what is the switching frequency of the charge pump? I think it was related to a slide where you were showing MPQ 58165. So what is the switching frequency of the charge pump?
The switching frequency of the charge pump in the 5816, when I remember, is approximately 2 megahertz. I'm not very sure. I don't have this data sheet in my mind. But of course, the charge pump switches higher. It must switch higher than the gate booster. And you find a data sheet for the 5816 when you get the data sheet from us about the EMC of this charge pump. We measured it. It's safe for CISPA 25. And for the gate booster, the switching frequency, it's depending much on the AC superimposed. It can be only a few kilohertz, but it can be also 100 kilohertz. When you apply 100 kilohertz, and it can be 200 kilohertz approximately. It's depending on the load and on the gate activity.
Okay, thanks a lot. The next one is, Why is the MPQ5816 not called diode regulator, similar to the buck controller regulator?
We called it diode controller. It's also regulating the internal voltage between source and drain to 20 millivolts. By principle, it is the same regulator like the other parts. It's a little bit improved because it's a newer one, but it's the same principle. The difference is only the internal MOSFET versus the external MOSFET and the gate booster versus the charge pump. But by principle, the rectifier is the same.
Okay, thanks a lot. Next one is, could you use machine learning to optimize parameters, values of the circuit for better output, and how to use it?
We don't have a software for this part, because what you need to do is you have to define your LC output filter, especially the output capacitor, your output load, the current, and the definition of the input voltage of the AC. It's a matter of the energy you need on the output and the energy the electrolytic can supply.
Okay, thanks a lot. And next one is, I think you already answered this one, but perhaps you can quickly summarize again. The question is, what about EMC PCI tests?
EMC is not a problem. You will see, just measure it. Because please always remember, this tiny boost inductor of 2 times 2 millimeter, it has not a big radiating surface. And when you place that tiny boost inductor very close to the IC, you have a small antenna loop. And it's the same for the charge pump, for the capacitor. These are not power devices. And always remember, the EMC measurement is done under DC conditions and not under failure conditions. An AC superimposed, I cannot call it a normal operating condition. It is a failure condition. And I don't know any EMC measurement which is done under a failed power supply condition.
Okay, thanks a lot. Next one is, can the device measure and or limit the input current?
No. Can't.
Okay. The next one is, hello and thanks a lot, Ralf. Is there some IC level EMC testing done by, for example, FTZ? Did you do some tests yourself in your lab, especially BCI testing? Is your MOSFET sometimes switching off during those tests?
Can you repeat the question, please?
It is there some IC level EMC testing done by, for example, FTZ? And then another one is, did you do some tests yourself in your lab, especially BCI testing?
I don't know. We must forward this question to the product line. Can you make the contact with the person who made the question? We will answer it.
Okay, yeah, we will send some information via email. Good. The next one is, it's a long one. Negative TVS is needed for the automotive isotransient pulses in order to protect the FET for the exceeding the breakdown voltage. Output capacitor is charged to, for example, 16 volt. So a negative voltage can generate a VDS above the breakdown voltage and damage the FET. So the negative voltage must be clamped to below VBR DSS VLOAD.
Yes. For automotive, it's highly recommended to use the negative TVS. If you have a battery management system and you don't have automotive specification, it's not always required to use the negative TVS. But then, of course, you need to know exactly what you are doing with your harness and with your test conditions. Sure, for automotive, use the TVS depending on your test level. When you have negative pulses, like LV124, use it. We have these questions because we have customers, they say, they see in the application note and in the data sheet, you have a negative TVS, and they say, I don't need it because I don't have reverse polarity protection into the negative. Or whatever, I don't have negative transient pulses. Do I really need it? I say for LV124, yes, you need. For other ones, it's depending on your harness and your conditions and on your load current.
Okay, thanks a lot. The next one is, are there also circuits from MPS which control the inrush current pulse?
It cannot be a diode controller because when you control it, then you have a loss on the MOSFET. I'm not sure, maybe we have something in the under development or under sampling. Also, please have contact to the customer. We can forward this question to the product line if we have such products.
Okay, thanks a lot. And the last one is it really O/ring and not OR/ing?
The Oring, it's hot swapping. You can apply and disconnect living power supplies under load. It makes no difference. So the Oring is really it's a very easy application for the diode controller. You can use 10 power supplies, 20 if you like, of different voltages. You can do whatever you want on the V source. The device is acting according to the difference between V source and V drain.
Okay, so at the moment, I do not see any other question. We will pause here for a little bit to give you the chance to type in any other question you might have. As already mentioned before, we are recording this webinar, and we will send you a link to the presentation and to the recording in the next couple of days. So does anyone have another question? Yeah, so it seems like no other questions are coming in. And with that, I want to thank you for your time. And I also want to remind you to look for future webinars that we are producing. Hopefully, we will see you back here again in the near future. And yeah, thanks again.
Thank you from my side to everyone.
Thank you. Bye.
Bye.